Welcome to today's webinar. The topic today is geotechnical analysis with construction stages in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the Dlubal website, the German and English webinars, customer projects, etc. I've been working for 12 years in the company Dlubal Software. I will be the moderator and answer your questions together with, it's not Alexander Meyerhofer this day, it's Markus Baumgartel, and the presentation will be done by Juliane Stopper-Aktak, but yeah, my colleagues can introduce themselves.
Hello, welcome. Yes, my name is Juliane Stopper. I'm working in the Dlubal team in customer support, and I'm also working for the developers team for geotechnical analysis add-on, and I'm supporting the developers of add-on concrete design. Yeah.
Hello, my name is Markus Baumgartel. I'm responsible for customer support and frequently asked questions on our website. And today I will help my colleagues to answer your questions during this webinar.
Okay, thank you for your introduction. Then we can switch off our webcams that the attendees can see the full screen. You can ask questions via the control panel on the right side of your screen. You can show or hide it with that arrow here, and you can enter your questions here. If you don't get an answer during the webinar, because there are too many, you will get an email afterwards. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's all from my side. I hand over the screen to Juliane and she can start with her presentation.
Okay, thank you, Andreas. Can you see my slides?
Yes, yes.
Yes, okay, great. Then I am starting now. First of all, we can have a look at the agenda for today's webinar. We will at first have a short theoretical background we will have a look at. After that, we will go into the program and work with a model. We will define the input for construction stages and geotechnical analysis. Then we will have a look at the analysis and the results and finish that model. Then we will have a short example for showing the modeling of uneven terrain. And after that, I will provide a short outlook, and this will be it for today. Okay, then we can start with the first point. We will go to the theory. One of the main features of the add-on geotechnical analysis are the special soil material models we provide with that add-on. And I will give a short overview about the main mechanical soil material properties. And I want to show the importance of modeling the construction stages when you work with finite element analysis for soil material. Okay, therefore, the first slide, we can see soil material models in the graphic. On the left side, the behavior in the triaxial test is shown. On the right side in the compression test. And we can see a linear elastic, perfectly plastic model like more Coulomb. And we can see an elastoplastic model, like hardening soil model. And with this model, with the elastoplastic model, I want to show these properties I listed here. The stiffness of soil shows a stress level dependency, which we can see here. If the stress is changing, the slope of the curve is changing, which means that the stiffness is changing. We also have a stress path dependency of the stiffness. There's a difference between first loading and unloading and reloading stiffness. the unloading and reloading stiffness is higher than the first loading stiffness. And we have irreversible displacements in soil materials. We have hardening effects and plasticity when the failure level is reached. Okay, so what follows from these properties is that we don't have explicitly for a stress state, a strain state. There is, for one stress state, there is no clear, no explicit strain state. Yes, and I want to show this with this graphic. What we can see easily is that if we have a look at the soil and we have a look at an element that is placed here, the soil is surrounded by weight of other soil, and its weight. So there is already some stress on the soil. And as we see from that model, if the stress is changing, the stiffness is changing, so we need to consider the stress the element is in already caused by the surrounding soil. So this is what we do in the analysis. We calculate first state of the soil, the initial state, where we only calculate the geostatic stress. Because as we can see, that if we start here, if we consider this geostatic stress, we use the correct stiffness modulus. If we would start here from 0 and not consider the stress, we would use the wrong stiffness. If we now think about that we want to apply a load, there comes a load on our element, then we can see the stress path dependency. If the soil is reaching this level of load the first time, it will use, or it will deform with the stiffness of the first loading, and we will have this strain. If the element had a higher loading before, or at least the same loading or a higher loading, and was unloaded, and like this it reached the current stress state, then it will use the reloading stiffness modulus, and we will have another strain. So I want to show it with that building. We can now see that if you want to, for example, model a project like this, you have the soil and you have here the excavation, and then you construct your building. Then you cannot just model the soil with the hole and the building in it and putting on loads. You cannot only calculate one loading phase because you wouldn't consider the path. You should at first model the whole soil and calculate it. Then you have the geostatic stress. Then you should model the unloading, so that you consider that it was before under higher loads and that you know you are now on the unloading and reloading path. And then you should start to put the construction, and you should consider these phases. Yeah. So in finite element analysis for soil material, the construction phases are considered. In the analysis, you need to do this for reaching the realistic results with these material models. Okay, and for this we have in RFEM 6 our add-on construction stages, and I will show you now how to create the input in the program, and we change to the program. Okay, so here we see the model we will work with. It is a prepared concrete structure. It is prepared because we want to focus on geotechnical analysis and construction stages analysis in this webinar. And I used this in the previous webinar, but today we will use another material model. and learn some details about this. And we will use construction stages. And then you can easily see differences in modeling process if it's the same structure. Okay, now we start. At first, I will go to the base data and open the dialog. And here we have the register for add-ons. And we can find the geotechnical analysis in the special solution add-ons list. It's activated, and I need to also activate the construction stages analysis in the analysis add-ons. And I agree. And now our main program, RFEM, the finite element program, is got some more input options and calculations and output options for these add-ons I wanted to have included. Yeah, and now we can start to define the data. At first, I will go to the materials. We open the dialog, and here we can enter our soil materials. We already have the concrete and the reinforcement steel. I will now create a new material, and it will be my first material. It's a fill layer, which is sandy, and this is the name of the material, and what we need to edit is the material type. Here we have soil provided, and we need to change here. I mean, we need to set here the soil material type. Only if the soil is chosen or selected, the soil material models are provided, the specific. As I said in the last webinar, I used the modified mock-column. Today we will use the nonlinear elastic model. Okay. On the right side, we have the option to enter the basic material properties, or we need also to enter them. I will start with the Poisson's ratio. I got them from my geotechnical report, and the first layer was tested to have a drained specific weight of 17 and a saturated specific weight of 20 kilonewton per meter cubic. Okay, so these are the basic properties. Now we have another register which opened especially for this material model, and we go here. Here you can see the data you have to fill for this material model, and before we start to write the parameters, I want to jump into the slides again because I prepared something for this. As you can see, I showed the dialog again, and here is you can see the equation which is used in the program to calculate the stiffness stress dependent. And these are the parameters the model needs. The equation needs for give the right stiffness for each element in each situation. We have here our stress. This is the variable value which the program calculates in the analysis and fills for every element, every situation specifically. We have the cohesion here, and we have the friction angle, which we know. What we need to have also is a reference value of the stiffness. We need one value of the curve, which is given for one reference stress. We fill here the reference stress, and this is the reference value of the oedometric modulus is the value we also need to give. Yeah, and with these input parameters, we can calculate the oedometric modulus for each depth for each stress condition. And we also have this parameter. It's the power for the stress level dependency. This value generally moves in that range. It can reach between 0.5 and 1.0, 0.5 for sand and 1.0 for clay, somewhere in between. Okay, now I want to show you the example I want to use today. Here I have my material properties that are provided from the geotechnical report. We have the specific weight, the drained values, and the effective values. as we know, the effective values result from the difference of the saturated specific weight and the specific weight of the water. We also have here the cohesion and the friction angle, and we have the stiffness, the oedometric stiffness that was tested for this soil. And what we need to do now is we have to adjust our material model with the parameters so that the equation provides the behavior like it was tested. And this I have shown here in the diagram. We have in the black dotted line the results that are given from the report. And I adjusted my parameters so that I have the blue line from the material model, and we can see it fits quite well. I filled in the M value here for sand. It is 0.5, and I used a reference value for the stress of 100 kilonewton per meter square. Then I checked that the result fits to the tested stiffness oedometric modulus, and it fits quite well if I use the reference value for the oedometric modulus like it is shown in here. And these values I can now enter in my dialog. So therefore I switch again to the program and we start to fill in the parameters we need. We have a cohesion of 0, but it is recommended by the geotechnicians that we provide a small cohesion just for stabilizing the calculation, even for non-cohesive soils. And I give 1 kilonewton per meter square. We have for this layer a friction angle of, we can have a look, of 30. I will fill in. We have 30 degrees, and we have the oedometric reference stiffness of 24 for this layer, and as I said, I use 100 for the stress, reference stress, and 0.5 for the power. I apply this, and I can see it here that it is defined. Now I copy this layer or the material 3 times, as I in sum have 4 materials. I changed the name. We here have a sand, call it S1. We have here a layer of till, which is between the sand layers, and I have here another layer of sand, call it S2. Okay, now I'm changing the parameters. We have here a specific weight of 18 for the drained specific weight, and the saturated value stays the same. We again have the 1 for cohesive strength, and we have a friction angle of 32.5 and an oedometric value, oedometric modulus for the reference stress of 40, and the reference stress stays the same and the power stays the same. Then I can enter my till characteristics. I have 21 for drained specific weight and 21 for specific weight for saturated situation. Okay, then we go to the material model specific register. We have here a smaller friction angle of 27.5 and the stiffness of 30, and we can assign this, and I will go to the last layer. Here we have 18.5 for the drained specific weight and 20.5 for the saturated specific weight. So I have here 35 for the friction angle, and we have 58 for the stiffness. What I forgot is here I didn't change the cohesion. We have in the till layer, of course, cohesion, we have 15 kilonewton per meter square. And this is it. These are my materials. Now I can see that they are defined in the model. And as the writing is in blue, it means these materials are not used yet in any objects. It will change later. It will be black like it's up there. Okay, then I'm having a look at my basic objects, and I can see I don't need another basic object. We can go to the special objects, and here we find objects we can use for the Geotechnical analysis add-on. We have here the boreholes. I will create a new borehole. In this dialog, you can enter the boreholes that you received from your geotechnical report. There were tests done, and you have information about the boreholes, and you can enter them here. I will now create one borehole. Therefore, we have to, you can also enter a name here. I will keep the default name. You have to enter the position. It's the top position. I will keep the 0. Then you can activate groundwater if you have one. For my situation, the groundwater was found to be in 3.9 meters depth. I agree this, and then I can start to define the soil layers. In the upper layer, I have the fill, then the sand follows, then I have my till and the second sand layer. And these layers reach depth of as follows. We have 4.8 meter for the first layer, 7.5 meters for the second layer. We have the till, which is 3 meters height, and we have 15 meters we will use for the last layer. Okay, now I defined all the information that is needed for my special object. For my soil borehole, and I can see it's shown here. I want to remove this grid. It can be found here, and I can set it to be not visible. Okay, so now I can create the soil structure. It can be found in soil massifs. I open it. And here we can generate the soil structure from boreholes. And for this, we have to assign the boreholes. In here, we can write the number directly, or we can use the graphical selection. We have to give the position of the massif. It's placed in 6 meters in X direction and 8 meters in Y direction, and it shall have dimensions of 48 meters each direction. Okay. And I have the option to activate the groundwater. We have groundwater. We want it to be considered, so I activate it. And now we gave all the information that needs to be provided for generating the massif of the borehole. And with the generation of the massif, the groundwater surface also will be generated. Okay, I say okay. And here we can our soil massif. And we can see quite well the groundwater level surface. And I will set the solid model, and I will go here to the navigator display where you can set display settings. And I want my model to be displayed in the colors dependent of the property, the material. Okay, now I can see the soil layers quite well. They were generated from the information that comes from the borehole. Yeah, and if we would have more boreholes, it would use spline functions and NURBS surfaces to generate the different layers, surfaces between the different layers of the massif. I showed this more in detail in the last webinar. Today I only want to use one borehole. Yeah. Okay, now we have the massif, and the massif generated soil solids. We have here the soil solids. We have 4 solids, for each layer 1 solid, and it, as we saw, generated the groundwater surface, and it also generated the surface supports. The massif, we can see the surface supports and types for surfaces. Here we have surface supports. The blue ones I don't need, and I will remove them. Yeah. Okay. Yeah. We have surface supports for the vertical surrounding surfaces that are sliding supports, and the bottom surface is has fixed surface support conditions. And as we are here, I want to use these supports. I want to create a object selection. For this, I select the surface supports and I can go to Edit. And here we have Select. And here we can see related objects. And now I can see that all the surfaces that are related with these surface supports are selected. I can do a right click on here and say Create Object Selection. And I will give it a name. It's the boundary surfaces. This selection I later can use it, and I can see them here in the guide objects. I have my object selections, and always if I want to use the boundary surfaces, I can go here and I have them. Okay, now I want to go on. We defined the structure of the soil. We have our building, we have the geometrical boundary conditions. Now we need the load conditions. For this, we go to the dialog for load cases and combinations. I just shortly want to show you the loads which I prepared. We have here, I want to start with the last load case of the list. If we activate the add-on Geotechnical analysis, we have a special action category provided called permanent soil. If we activate this action category, the self-weight that is activated uses only soil solids for the self-weight calculation of this load case. So this is the load case that calculates the self-weight of the soil and that we need for the geostatic stress calculation for the initial state. Okay, and then we have here in load case 1 the self-weight of the building. Here we can now see that the self-weight is activated except of soil solids self-weight. Yeah, and then we have dead load and live load, which are prepared in that model. I can have a look at them. We have here the live load, here the dead load, and yeah, I can deactivate the loads with this button. Okay. What we have also is we have some special mesh settings. We can find them in Calculate. Here the mesh settings are placed, and we have the general settings that contain the target length of the finite elements for the structure. And we have the option in solids to activate a special target length for finite elements of the soil solid, as it is much bigger and needs larger elements. So this I wanted to show you. We keep the default settings. Okay, now our structure is prepared and we could do the finite element analysis, but we want to use construction stages, and these need to be defined now. As we can see here, we have this point in the navigator, which came by activation of construction stages analysis, and I click on New Construction Stage and come to the dialog. In this dialog, I have to define which objects shall belong to a construction stage or shall be considered in the calculation. And this is my first construction stage, so it will be the stage where only the soil solids self-weight is calculated. And for this, I need to do a change in the solids, and I need to do a change in the surface. I have to consider the boundary surfaces. So by activation of them, the special registers were opened, and I can here add or deactivate solids, and I want to consider all solids in this construction stage. Now they are selected. And here I want to add the boundary surfaces, and for this I now can use my object selection. I have prepared it, and I can click here and it is added. So now my surfaces for the surface supports are added. I also add my surface for the groundwater level, which is surface number 27. Okay, I apply this and I have my first stage defined. Then I define a second stage. This will be a stage where I will change something in the static analysis settings. I will show later. In this stage, I don't want to change anything in the structure. I still only want to have soil here. So I don't need to change something. I can deactivate these fields. Now I can create a third construction stage. And here I want to add my building. So what is contained in my building, I need a change in the members and in the surfaces. And I can, in the dialog for members, I can say I want all members to be considered and I want all surfaces to be considered. Now it is okay. I have created 3 construction stages and I can see them in here. The program reacts more slow due to the use of the GoToWebinar. Okay, I have something activated. Show hidden objects and background. I don't want this. So now this is what we have. We can see what we have in the construction stage 1. It's the soil as I wanted it and the groundwater level surface. In the stage 2, I wanted to have it like this as well. And in stage 3, my building will be activated. This is the topology part of the construction stages. Now I also have to set the loads, which loads shall be active in which stage. I have to give this information. For this, we have here the construction stages input placed. I go to the dialog and I can see the stages listed here as well, and I can do load settings for them. So we are now in the first stage. And we have here the register load cases. And here I can say that I want the self-weight for soil to be considered. Okay. In the second state, I also want only the self-weight for soil to be considered. And as it is a permanent load, it is already there. It comes from stage 1. In stage 3, my building is placed and I want the self-weight of my building to be considered. And then I create a next stage. In this stage, I want the dead load to be placed. And then I activate or create another stage. In this stage, I want the live load to be used. Okay, so I have 5 construction stages in my model. What I need to do is now set my second stage. In this stage, I want to reset the displacements. If we think about the first stage, in that stage we calculate the geostatic stress in the soil solid. And we also receive from this geostatic stress displacements in the soil solid. But I don't want to see these displacements in my results. I want that when my construction of the building starts, this is my 0 point for the displacements. Therefore, I reset the displacements of the geostatic stress state. And I will do this in the second stage. We have the special feature for resetting the displacement in the static analysis settings. That's why I open them here. And our SA1 is the static analysis settings we use. I also change the load increments as we use the nonlinear material model. I want the load to be put in increments. And as I entered the 4 here, I now have the option to save results of all load increments. I want this to be done. Okay, this is my basic setting. And now I create a copy of it because I want to create my special setting for my construction stage 2. In construction stage 2, I will use the equilibrium for undeformed structure. This option sets that in the calculation is done with the loads, but the deformation is always reset to 0. Okay, I agree to this, and I need to now change this for my construction stage 1. And the color here gives an overview about that. Only in this construction stage 2, I use another analysis setting. Okay, now I finished the preparation of my stages. I can also see now, if I activate the load display, I can see that here the loads are added. Okay, now I am ready to start the calculation. I won't do this now. In order to save time, I prepared a model which is finished, which is calculated, and we will have a look at it with that model. I get it to here. It's a bit slow. Okay, so here we see the equivalent model after it is solved. We can see now the first construction stage, and we can see the navigator results, and we have here solid results. And I will at first show the sigma z in z direction. And this is the stresses we receive only from self-weight of soil. This is my initial state. From that, we start the construction. As I said, these stresses cause, of course, global deformations. We can see them here. And I don't want these deformations to be displayed in my results for my structure. That's why I reset these displacements in my second stage. And now we can switch to the second stage. And we can see that it worked quite well. We have no displacements now in this, no deformations in this soil solid. When we have a look at the stresses, we can see that we have the stresses. So I reached what I wanted. I have the stress considered, but the displacements are reset. Okay, now the building can be put on the soil. And I can see my global deformations only caused from the building. Okay, this is as a short overview. Now I want to show some more stress results. This is my stress in Z direction. After the construction is built and the self-weight of the construction is considered. I here have also my dead load assigned, and we can have a look at the load. And in this stage, stage 5 is my last stage, I have also the live load assigned. And this is my total stress at the bottom of the solid. And if we compare the stress received at the bottom surface with the stress from the initial state, we can see that the stress changed only by 1%, round about 1%. So the distance of my building to the bottom surface, for example, is far enough. What is also of interest for us is the contact stresses. Therefore, I will go to the wireframe model view and so show this perspective. And as we can see, the result is not easy to analyze as the high stress values of the solid are considered. And therefore, we have to show, we have the option that we get differential results only for stresses of the building, because now we know that in our whole structure, the result of the stresses of the soil self-weight is considered. And if we check the differential result, only the result of the building, we can see the contact stresses from the structure. Therefore, I prepared load cases. This needs to be done for load combinations I prepared. I will only shortly open this dialog. I can, in this webinar, only give a very first introduction into the add-on construction stages. We have extra webinars about construction stages analysis, which my colleague Mr. Langhammer is giving, and also there's another one from Amy Heilig. There you can follow the definition of the load combinations more in detail. In this load combination, the construction stage 3 is considered, and its initial state is construction stage 2. And now I can check the differential result, which is the result between this load combination and its initial state, which was the load case or the stage that considers only the soil self-weight. So now in here we only have the self-weight of the superstructure and its effect on the soil. I will have a click here and again here. Yeah, and now it's more easy to check the contact stresses below my building. Yeah. Okay. I also want to show another display type. You also can use this ISO bands for solids. And I can have a look, for example, to principal stresses sigma 3. And now I can see how this building self-weight affects the soil solid. Yeah, this I wanted to show you. Now shortly also I want to go back to the displacements or deformations. We can go here and have the isobands display type. And now I want final results. And I can go back to the construction stage 4, which is the sum of all the building, of the dead load, of the live load. And we have a tool which is quite helpful for the analysis of the results. We have here in the guide objects the option to define clipping planes. I prepared one and I will switch it on. And I have a cut through my solid. I can define the plane in the position I want, in the slope I want, and I can have a look into the inside of the solid. And yes, what we can see in this graphic is that by considering the soil solid, the soil structure interaction is can be analyzed quite well. We can see effects like, for example, the surface here, the foundation slab and its settlements. It has an effect of on these foundations of the columns, and even these foundations have an interaction with each other. And if you want to change something in your building, or you need to change something, you need to change some cross sections or some stiffness somewhere, directly the effect is considered in your analysis and in the soil structure interaction. This is the benefit of modeling it like this. Okay, what I want to show you also is we have saved the load increments. So I can also have a look at the load increment results. I can activate it here, and then I can go from, for example, from 25% of the load up to 1. And I can have a right click in here and start an animation, and I can see how the building is settling. And this sometimes can be helpful in understanding the behavior. Okay, and having a click somewhere here ends this animation. Yeah, like this. Okay, I have another object selection prepared, which I can activate here in the visibilities. I deactivate the construction stage visibilities and activate my object selections. And I have here, for example, one prepared which only contains the soil solid, and I have another one which only contains the building. This can be helpful if you, after you checked the soil results and you did your documentation, if you afterwards want to have a look at your building, you don't need always the whole solid to be displayed. You can just use this selection and then have a look at your building in detail, at the columns, at the surfaces and beams and so on. Yes, and for analyzing these results, you can use all the tools we have, like doing result sections and so on. Okay. This shall be it for this model. I want to finish the model now and go to the short example for showing some modeling techniques which you have for defining uneven terrain. Yeah. As I said, in this time of this webinar, I only could give a short introduction into the construction stages add-on. We have the special webinar for it, which you can have a look at. And in my last webinar, I had more time for the results. You also can have a look at the last webinar for seeing some more result analysis ways. Okay, now I close this model and we switch to the simple model for showing some modeling things. I have here more boreholes. As we know, they are in the special objects. And here I have my boreholes, which came from my geotechnical report. And my soil layers, they are different in the boreholes. Now I define my soil massif. I select my boreholes. I want to use those. I select them and I give the position. It's placed in 20 and shall be 80 meters in this direction and only 5 meters in this. I model it a bit like a stripe because it's more easy to see the effects I want to show. And as you can see, now the massif was generated and the soil layer surfaces were generated quite well from the boreholes. This is one option to model it. But if I want to model uneven terrain, it can make sense to not only use one massif, therefore I delete it. You can also divide it into separate massifs. Therefore I again go to the dialog and now I create a smaller massif, which is placed at -7. It is only 20 meters in A direction and again 5 in B direction, and I use the same boreholes. And I can activate this. Yeah. Now I see I have one massif here, and I can copy this and create a second one next to the first. Yeah, and for these small massifs, I always use all boreholes, and this causes that the soil layer surfaces still fit as well as when as if I would model it as one massif. Okay, what I need to show is if we generate the massifs, of course the surface supports are generated as well. I have deactivated the view. I will activate it. They can be found here. And I see that in the contact surface I have the surface supports. These I need to remove up to now manually. We are working on that. It will be automatically if there are neighbored massifs. Okay, now we can go to surface supports and say edit assignment. And here we can select that there shall be no surface support at these surfaces. And now it is fine. I go back to the solid view and again deactivate the display of the surface supports. Okay, what I can do else is I can define a new massif, and I want it to be placed in a deeper depth. I mean, I want the surface to be in a deeper depth. So I will do it like this. I will use a copy. I copy this massif, and it will be placed at 30 next to the previous one, and I will use other boreholes. For this case, I prepared a copy of these boreholes, and in that copy I set another Z value, and the height is different. So you will see the effect soon. What happens now is that this massif starts at the Z value of these boreholes. And now I have a different top surface level. And this is possible to do. And again, I did that. I don't need a new, I want a copy. I will put another massif next to it, and I will again use these, and the X position shall be 50. Okay. Okay, so now we have different massifs, and what we can do is we can, for example, use this technique if we want to have different mesh settings. For example, if our building will be placed here, maybe I want a more fine mesh in here, but I don't need a fine mesh here. So dividing it into different massifs can help to can make more flexible to create the mesh. And also I want now to edit the geometry manually, and therefore it's also helpful if I separate it like this. I can do this. So now we again go to the massif dialog. And as I said, these massifs were generated from boreholes, and the solids that are produced by them, they are they have a generated status, which means they are connected with the massif and with the boreholes. So if something in the boreholes is changed, like the material or the coordinates, the massif is changed automatically. This is the generated state. I can deactivate the state, because in the generated state, of course, I cannot edit the geometry of the massif. If I reached a modeling phase in that I want to change the geometry of the massif, I can change the soil massif type, and I want to do it for massif 3 and 4. I select both of them, and I can set the soil massif type to set of solids. Then the connection to the connection of the solids to the massif and especially to the boreholes is deactivated. So if I change something in the boreholes, these two massifs won't be changed, but it enables us to change the geometry. So I want to do this now. I want to have a slope in the surface, ground surface. Therefore, I need to put these nodes into the line. I want my line to be divided into parts at that node, and I can use this button therefore. and I select it. So now my line is divided. Now I can select this line and the two nodes and say, please move them in X direction by 6 meters. And I say, okay, now it is moved. It happened that a surface was disturbed. I can show, here it's red, it's invalid. I go to edit to repair it. And I will remove these lines as the surface cannot go around the corner like this. For removing it, I can press Shift. Yeah, I can press Shift and you see the minus, then it's removed from the list. If I don't press a button, a line is added. I can say OK, and now I have fixed my surface and I can create a new surface for this area. We need the surfaces for defining the shape of the solid. So I need the select boundaries and I changed the stiffness type to without thickness. I don't need a thickness in this surface. It only shall define the geometry for the solid. Okay, now I have a surface here and I also have to change the solid. As I can see, it's also red because the surfaces were changed and I have to add the new surface I defined. Okay, and now my solid will be fine as well. Okay, I'm deactivating this massive shape. Okay, now we can see, if we look at the solid model, that we also have now the slope, and you can do everything. You can add surfaces that you want, you can add nodes, and you can edit with all the tools we have for modeling. You can edit your soil solids shape. I want to show you another helpful tool we have for modeling with solids. We have the option to define intersections. I will therefore create another surface without thickness, which I want to place here. And I move this node, this line, and this node in X direction, maybe like this. Okay, now I have here a new surface and I want to extrude it into solid. If I do a right click on it, I have here the option to extrude and can create a solid directly from that surface by extrusion. Yeah, and here I have to enter the height of the extrusion and I can say apply, and then I can see that a new solid is placed here. And the solid is in my list here, the last solid. I can open this solid and I can see that my solid type is standard. I don't want a standard type solid. I want an intersection solid type. This solid shall give the shape of the intersection and I say OK. Now I have my intersection here, and if I have a solid intersection in my solid, I can cut them. So I select this layer, do a right click here, can go on solids, and here I have the option to choose cut by solid intersections. I get a warning and I say OK. I agree, and now it's cut. It's really slow because of GoToWebinar. It wouldn't be that slow. Okay, now my solid is cut. I have divided this layer into this solid and this solid. Now I want to delete this to show you that it worked. Yeah, I used this solid intersection in order to cut a shape that was defined by the intersection shape into my solid. Yeah. Okay, this was it. These were the short modeling techniques I wanted to show. As in my work in customer support, I received questions according this topic several times. So that's why I showed this small model. Okay, this was it from my side today from the for this webinar according the geotechnical analysis and construction stages. I said I want to also give a very short outlook. We are working in the development currently, especially on finishing the hardening soil model so that we can provide it to the customers for the analysis. And we also work on pile foundations. This is one topic we are working on. Yeah, and then we also work on topics related to the massive definition in order to improve it. Yeah, like this. Okay, then I want to show you also, I have in the slides, I added a slide with links. Here you can find links to the webinars I would recommend about construction stages. And we also have online manuals where you can, for example, for geotechnical analysis, find some information about the material models. Yeah, you can check them. These slides will be provided by Andreas. He will show you later. Okay, this was it from my side. Andreas, I would give the word back to you.
Okay, thank you, Juliane, for this nice presentation. Yeah, at the end of the webinar, I would like to show you where you can find the recording and the models and the PowerPoint slides. I take over the screen, just a moment. On our website, dlubal.com, you can find under News and Events the webinars. We record all our webinars. Those are the upcoming webinars, and this is today's webinar. I just click on it. In the next days, you will find the recording here in the middle, and you already find the presentation slides here and the models. Yeah, and together with the recording, you can go through the webinar again with recording and model or something like that. If you don't have already RFEM 6 and the add-on geotechnical analysis, then you can download our free trial version. Here above, you can find the link. And then just download the RFEM 6 trial version. You can test the full program for 90 days with all add-ons, also the construction stages add-on and all the other add-ons. Okay, then we are at the end of the webinar. I would like to say thank you for your attention. Thanks to Juliane for this nice presentation. Thanks to Markus Baumgartel for his help by answering the questions. Maybe a last hint, when you leave the webinar, there is a small survey. It takes you only 1 minute or so. You can score the webinar. Just note that the worst score is 1 and the best score is 5. You can enter your wish for future webinars or something like that. If you don't want to answer the question, just enter a minus or slash or leave it empty as you want. Okay, then have a nice rest of the day and bye-bye.